All right, LeetCode 1261, finding elements in a contaminated binary tree. So kind of the important things to notice, root.val is equal to 0, and if we go down here, tree nodes, there's always at least one. So we never have to worry about giving like a null node to start with. We always have at least one node that's valid. Okay, and we have these two rules. If a tree node.val has a value x and it has a left, so it has a left child, then the left child's value should be 2 times the current node's value plus 1. And then same rule if it has a right child, except the right child should be 2 times the current node's value plus 2. We're given the tree contaminated with all values changed to -1. So we're given the tree's structure, but we don't have any of the values. So we need to go over the tree and change the values back to what they're supposed to be using those two equations. So let's just sketch this one just to kind of visualize. So we kind of have a tree of some structure, doesn't really matter what, could be anything. Maybe we'll do something like this. And for each node we're given, so we're going to start at this root node. Well, we know this one is always going to be 0. So we can just initially set it to 0 and get rid of the -1 that's going to be here because they're all going to be set to -1 initially. Now we need to go and see if it has a left child or a right child or both. And then we say, well, if it's the left child, then we're going to do that left equation. Left is 2 times x plus 1. And if it's a right child, we use the right equation, 2x plus 2. Okay, so in this kind of scenario I drew here, 0 times 2 would be 0 plus 1, so this left child would be set to 1. And then for the right child, same idea, it'd be set to 2 though, because we'd use the other equation. Now, same thing, except we have to kind of go further in the tree, so we have to go deeper. So now for this child, we need to see its left and right child, and we need to say, well, 1 times 2 is 2 plus 1, so 3. And then for the right child, 2 times 1 is 2 plus 2, so it would be 4. And then we'd go over here, and then 2 times 2 is 4, plus 1 would be 5. And then we don't have a right child, so we just go back. We don't do anything when there's no child. Okay, so let's kind of think about this in code. So we can kind of do the find first, because that's kind of the more complex. So let's just do it recursively first. Because we have these two different equations for if it's a left or a right, let's just keep that really clean and say find left. So we'll have two different recursive algorithms that do basically the same thing, but they handle if it's a left call or a right call. So we'll say find left, find right, and then we'll just use that parent that we're given to handle the very base case for the first node. Root. Oh, sorry about that. Node. And then we're also going to need the last node's value because we're going to have to use it for the calculations. Because the two equations use the previous node's value to calculate what the current node's value should be. Okay, so now we have these two. What do we need to do first? Well, we know we always have a root, so we don't need to test if it's null. But we do need to say root val equals 0 to get rid of the -1. Otherwise, all our calculations will be wrong, and traversing the tree will just give us a bunch of wrong values. So once we set it to 0, then that's when we can call. We need to solve the left subtree and the right subtree and change each node's value to what it's supposed to be based on the values we're going to pass down the tree. So we'll do find left and do a recursive call to this algorithm. We'll give it root.left, and we'll give it root val. So it has the current node's value at the next depth to use for its calculation. And then find right, root val. And you'll notice that the right and the left are basically identical except for the equations that differ. So we call find left and find right, so we go down the left and the right subtree of the root node. And then for each of these calls, we're going to say root val equals, well, for left, it was 2x plus 1, with x being this val that we got from the previous node. So we'll say 2 times val plus 1, And then for right, it's going to be root val equals 2 times val plus 2. But kind of the same concept. So we set the val in the node, and then now we need to recursively go deeper in the tree and do it for the next node. So we still need to check the left and the right, because even though this was the left node of the node it came from, it can have its own left and right child. So we have to check both subtrees. So we'll say root left, root val, and I skipped a step here. I forgot to add the base case. So we'll add that after this. Root right, root val. So since we are not checking when we make these calls to see if it has a left or a right child, we need to check that when we get to that depth. So if we call this and this is a null pointer, like this node doesn't exist, we can just say if not root, then we just return. And these should be void returns, because we're not actually going to be returning anything explicitly. We're doing everything kind of through this tree node pointer. So void, void, okay, and then same for right. So if we don't have a root, then we pass a null pointer, which means that the right child doesn't exist. We just return. So 2 times val plus 2, and then the same thing, we need to recursively call in right. Now, that will fix the tree. We'll go down each subtree and do the value calculations depending on which method was called, and then we'll recursively do the next depth. And once that finishes, the tree will be correct based on the rules. But this find is going to be really expensive if we don't add some stuff, because we're going to have to traverse the whole tree looking for a value every time we want to do a search. But while we're building the tree, we already are going to have to see all the values that are in it. So while we're here, we can just do unordered set. You could also do like a vector, but that's not really efficient, because then you have to loop through the whole vector to look for the value, whereas the set, you can just use contains to check it. So unordered set int, we'll just say vals. And then every time we see a root val, like we get the final value, we just push it into this vals set so we can check for it later. So we'll say vals.insert root val. And then the same thing, once we do our calculations in the children, we just add it there as well. So we have all the values of all the levels, and then we can just check the set instead of having to traverse the tree each time. So let me just check that over. That looks good. And then when we get to target, now that we have this set, all we have to do is say return vals.count target. So if the target value is in the set, then it's going to return true, and if it's not, it's going to return false. So let's give this a quick once over. I think that looks good. Let's give it a shot. Missed some. Oh, typo here. Root val. There we go. Now if we submit, so decent, but kind of slow. And it's because of the recursion. Also, the memory could be better as well. The recursion just adds a lot of time, and it adds a lot of memory from all the calls. So we can actually do it a little more efficiently if we do it iteratively using like a DFS algorithm. And it's the same exact concept, we just have to kind of rearrange some things. So we're still going to store the values for later with the find. So we'll do unordered set int vals. Now we're still going to use this kind of as the parent. So we'll say root val equals 0 under the same premise before, like it's always going to have a root, and the root value is always going to go to 0. And then we'll say DFS tree node root, and then we'll need to implement a DFS. So essentially what we did a minute ago was a DFS. We just did it recursively. This is going to be iterative. So tree node root, and then this can just be root. Actually, don't need the type there. Tree node root. And then this is going to be void as well, because we're still doing everything within that kind of root pointer. void. Okay, so we get the root. Now, since the first root that we pass is going to be already ready because we set the value to 0 already, we're going to do a queue of tree nodes that we need to check. Call it queue. And then we'll say queue dot push roots, because root's good to go. And that's where we start our iterative kind of search. So we'll say while not queue is empty. So while there aren't nodes in the queue to check for children, we're going to keep looping and keep checking. So while queue is not empty, we're going to say tree node per equals pointer. Queue dot front, which is the node at the front of the queue that needs to be checked next. And then we'll do queue dot pop. Once we check a node, we don't want to have to check it again or accidentally make changes to it, so we just take it out of the queue. And now we're going to check if it has children so that we can get them ready and get their values corrected and put them in the queue to check if they have children. So we'll say if per left, then per left value, so the left child's value equals per val times 2 plus 1. So the equation for the left child. And then once we do that, then this left child is ready to be added to the queue to be checked for its children because its value's already been handled. So we'll say queue dot push cur left. So the left child gets pushed into the queue. And then the same thing for right. So we're actually just going to copy paste this. If it's got a right child, then we're going to do the same exact thing, except we're going to use the other equation 2 and then queue dot push right. And then I believe we're good because we're going to push these in and then they're going to get pulled and then they'll get set to cur, they'll get popped. We'll check their children, set the values. And then when the queue is empty, then that means we've seen all the nodes that are in the tree. And then it'll just break out. So we should be good there. Yep. And then same exact thing because we added them to vals. Oh, we haven't added them to vals yet, so we need to do that. So we need to do push root. We'll do that right here. We'll do vals dot insert per val. And there we go. So now every time we pull a node that we know we've already done the calculations for before, we will add its value to the vals set so we know we have it. Okay, so now that's there. Same thing as before, return vals dot count target. Boom. And we should be good. I think we're good. Yep. And now you'll see this is a lot quicker than the recursive algorithm. Yeah, we're looking at like 95. So a big improvement, just because we don't have to deal with all those recursive calls and stuff like that. It just saves a lot of overhead. But yeah,